talking about these. Okay, I'll be talking about the verified log-free session channels, which is a project I worked on with my supervisor, Robbert Krebbers. So to start with, we're going to be discussing a specific type of concurrency, which is message passing concurrency. This is a different type of channels than we consider for the Go talk we had earlier. In this case, the channels just have two specific endpoints which we're using. And this is an approach you can use for communication in concurrent programming, such as in Rust, say. You can use Go channels for it as well, Scala, and that sort of thing. And as a quick example, for instance, we have a simple channel between a client and a sorting process. And for instance, the client can send 3 integers, one after the other, and then receive a list of those integers in sorted order back. But of course, if we have these channels, there's a few issues that we can encounter. So the first such issue is that we can send, for instance, the wrong type of data, which means, for instance, the sorting process can send back an integer instead of the expected list of integers. But also, we can send some sort of invalid data, such as if we're sending a reference containing a value, that we send an invalid reference, or we can even get more complex problems, such as these databases. So let's say we send a reference, but then immediately free the reference. Well, then we're going to run into a database. So we want some sort of safety to make sure that we're using these channels properly. And for that, we use some sort of protocol, such as, for instance, session types. Well, the thing is that current session type systems, basically they take these channel operations and they take them as primitives and prove safety with respect to these primitive operations. But of course, channels themselves are going to be implemented using a form of low-level data structures. So the goal of this is, of course, to verify a form of end-to-end correctness with respect to these low-level implementations of these high-level channels. And first, we're briefly going to talk about some background of these high-level channels and low-level implementations. So we're going to start with basic session types. So we're going to consider a few operations for these session type channels, and those are these. So we're going to start with an operation that allows us to spawn a new process that communicates over a channel and returns one endpoint of it. Then you can, of course, use one of those endpoints to receive a value or to send a new value, or there's a specific kind of operation that allows you to pipe in both directions between two of those channel endpoints and give up those two endpoints. As an example, here's a process that takes an integer and just returns its successor. Well, instead of using it directly, we can just start another process that sends a specific integer, in this case, 2 to it, and then immediately forwards the output to its own channel. And then we can receive that forwarded value on the main thread again. Well, we want to add some form of protocol, so for this we just use standard session types, and session types consist of these 3 kinds of constructors for types. So we can say that we're going to send a specific type with exclamation mark, we can receive a specific type with a question mark, or just mark the end of a protocol. And if we want to annotate the example from before like this, we can say, for instance, that the channel C, first we're going to send an integer, and then we're going to receive an integer, or for C prime, we're only going to receive an integer. Well, on the other side, we of course have the low-level implementations. So for this, we can consider considering channels with 2 endpoints, so we can implement these channels using 2 unidirectional queues. And of course, there are many different implementations for the queues themselves, such as singly linked lists. We can use array segments, ring buffers, a lot of different options. In this talk, we're going to be focusing on the singly linked list. So there's a few challenges with actually proving end-to-end correctness of these session type channels. The first is actually, well, we had that link operation which basically pipes between 2 channels, but how are we actually going to implement that in the low-level data structures? The second is proving the end-to-end correctness itself from these low-level data structures all the way up to session channels. And the third, well, we have a lot of different implementations of these queues. So we want a way to make the verification reusable so we don't have to start over whenever we're looking at a different implementation. So to start with, and the verification is done in Coq using the Iris framework. So to start with, we're going to be looking quickly at how we actually implemented this linking And we did that on the queue level rather than the channel level to make it a bit more reusable. So how are we actually going to be implementing this form of linking? Well, we're going to just start with a singly linked list. And then we have already this const node type and the nil node type. Well, for linking, let's just add an extra type of node, which does not contain a value, but it does have a pointer to the next node. And of course, if we're going to give a verification of this, well, we need some way to write a specification. So we're just using standard Horde triples for this. So in this case, if we want to link two queues, well, we're going to take two queues, and then after linking, we'll be left with one queue, which contains both the values of the other queues. But of course, we're doing concurrency, and Horde triples have a big gap in that the precondition holds before we start the function, the postcondition holds after we end the function, but anywhere in between, we have no idea what's happening. So we could have destroyed the entire queue and started build it again, or we could have combined them and then enqueued everything, dequeued everything. We have no idea. So we need something stronger than just standard Horde triples. And for that, we're using a stronger version, which is a logically atomic triple. And this has the condition that we have a single linearization point, such that before the linearization point at all times the precondition holds, and after the linearization point at all times the postcondition holds. And this means that even if you're using multiple operations concurrently, well, at any point in time, the queue structure itself is valid. So that was mainly how we implemented and started verifying this linking. And the other thing we're going to focus on in this talk is, of course, maximizing the reusability, because there's all of these different queue implementations. We don't want to have to build the session channel verification for each and every one individually. So, of course, if we're talking about reusability in implementations, well, we use decomposability, or we decompose it into smaller problems. So for channels, as I mentioned earlier, we're just going to start with the heap operations, then build queues, and then on top of that, we build channels. And standardly, if you give specifications, well, you start with the specification of your primitive operations, and then for each layer, well, you just give a specification for that. But that means that we still have to do a lot of work again. If we're, for instance, going to swap out the queue implementation, it generally happens that our channel implementation is now going to depend a lot on the structure of the queues to go from one layer to the other. So what we're instead going to do is we're going to split these in two. Our idea is, well, they're just Horde triple specifications, so we can give multiple for the same operations. So what we're going to do is we're going to split it up into having a specific low-level representation of just the data. So we abstract over the data and just build these, for instance, a representation of queues, a representation of channels that does not depend on the implementation. And then on top of that, we do the more interesting verifications in a higher abstraction level. So in our case, we have this form of ghost linking, and we have the session channels, which are just built on top of the data structure for channels. And as I mentioned before, this is actually where most of the interesting verification happens, so that's also where our two contributions are on the verification side. In this talk, we're going to briefly focus on how the ghost linking works and why we need it. So consider we had this logically atomic triple for the linking, and the thing is, with the logically atomic triples is that we said at a single instance in time, we're changing these two queues and merging it into a single queue. But recall, our channels are actually just two queues, so one in one direction and one in the other direction. And that means if we're linking our channels, well, we're just doing two queue linking operations, one for one pair of queues in one direction and one for the other pair of queues in the other direction. Well, now if we want to do anything with linearizability for the channels, we can't do that because we have two of these linearization points, one for one side of the channel and one for the other side of the channel. So we cannot directly give a logically atomic triple. Instead, what we're going to do is, well, we're going to think this linking, it doesn't really affect whether we can read or write to either of the sides of the queues. So instead, we're going to start with a queue or multiple queues, and we're just going to draw a bigger box around that and call the ghost queue. And now we're going to abstract basically over whether we have actually linked or not, so it no longer matters. In fact, if we now perform a specific linking operation, you can see in the representation, the queues are linked, but the ghost queue itself can stay the same. So that allows us to use it in the pre and post conditions of a logically atomic triples. In fact, we can just draw a box around any of the queues to create a ghost queue. As I mentioned earlier, now we can just combine two of those ghost queues by combining the two boxes without actually performing any linking. And what we're going to do is produce one of these extra tokens, which we can later use to link two queues in any of these ghost queues. And then, well, we use this token with a standard Hort triple because we no longer have to worry about the linearizability because the ghost queues are already linked. So how are we going to use this? Well, here's again the implementation of linking for channels. What we're going to do is we're going to start with these ghost queues. Then we're going to pick a linearization point just at the start of the function. And here we're going to logically link these ghost queues. So we're just going to change the boxes around our queues, but we don't actually perform any physical step. And this is where we go from the 4 ghost queues of the 2 channels to the 2 ghost queues of the combined channel. And we make 2 of these tokens. And then during the rest of the method, we just use these tokens to actually physically perform the linking steps of our queues. And as you can see, we have a linearizability condition because at any point before the linearization point, we have these 4 ghost queues. And at any point after this linearization point, we have the 2 merged ghost queues. So the neat thing about this ghost linking is that it doesn't actually depend on the specific implementation of our queues. So what we can do is you can just pick another implementation of a queue, verify that low-level specification of it, and then we can just reuse this ghost linking principle and anything that goes above that. For example, we have another example in the paper where we don't use singly linked lists, but we instead use some form of array segments. And the only thing we had to do to move from the singly linked lists to this version of queues is just re-verify the low-level specification of queues, and then everything from ghost linking all the way to session channels could be reused. So briefly, in conclusion, our main key idea is to actually have 2 specifications. One which is a low-level specification, which is more tied to the data representation that allows us to abstract over the implementation, similar to how you would use, for instance, interfaces for implementations. And then we build the higher-level abstraction layer to reason about more complex properties, such as this ghost linking or session types for channels. And of course, the main verification properties are these extra properties. So in our paper, this was the ghost linking and pairing invariants that we used for this. And we verified all this in Coq using the Iris framework. Thank you.
All right. Thank you. Is there anyone who has any questions? Now, while we are waiting. So this is very Iris kind of specific. When it comes to practical side of things, I'm just curious. How applicable do you think it will be? So I was just looking through the paper quickly while you were doing it. Yeah, that's fine. But it was basically quite low level to the verification of it. I'm just not sure when it comes to applying to the real code. How do you get there?
What do you mean in this case? Sorry. I can say at least one thing. So, of course, well, our mechanization is done in Coq using Iris, but at least the principles of just making sure that you use different specifications. So, for instance, give multiple Hort triples for the same operation. Well, you can use that with anything that you verify these Hort triples or logically atomic triples with. And that just gives you the same principle as using interfaces for programs themselves. You can give these kinds of interfaces for your host specifications instead. So that is a bit less specific to
I guess what I mean by practical is like if you have different programming languages with different basics. I mean, how widely applicable it will be rather than anything, but that's okay.
A lot of this is related to verification, of course.
Yeah.
If you can give this, in this case, some of the higher levels or higher abstraction layers are very either specific, but of course at the bottom level we just say we have some implementation of Q with some operations, so it's relatively, I think it's relatively plausible to swap it out for either another language or another implementation of Qs, and that is not very language specific.
Okay. Okay. Yeah, that's what I meant by practical.
Yes,
in terms
thank
of,
you.
Yeah, different languages. Okay. Sorry, that was an easy question. Like formal side, how does it apply to practice? So, anyone? No? Okay. Thank you.
Thank you.
Let's see if we can find more.